Hi, everyone. Welcome to section 3.6. In this section, we are going to be discussing modeling with exponential and logarithmic functions. And we're going to solve literally for the equation for a specified variable. So if telling us to solve for a particular variable, then we isolate the variable, we apply our properties of exponentials and solving equations for logarithms, and then we solve for the corresponding variable. On question 1, they're asking us to solve for d. That means we want to isolate d. The first thing that we want to do is bring this 23 over, as s minus 23.5 is equal to 2 log d. Now we divide both sides by 2, and we get s minus 23.5 over 2 will give us log d. Now remember, if I want to isolate, log d, I'll look like a 10. Log d. Now, if we're interested in solving for d, we need to change it to an exponential. So remember, if we're trying to solve it as an exponential, the base is 10, and there is our exponent. So it's 10 raised to the s minus 23.5 all over 2 will give us d. So we take the exponential of both sides. Now on the next question, question 2, they're asking us to solve for x, which is inside as an exponent. So the first thing we need to do is bring the t over, and we have 3 e to the nx is equal to 4.2 plus t. Now that we have it as that format, we divide both sides by 3. We have e to the nx is equal to 4.2 plus t over 3. Now to undo an exponential, we're going to take the ln of e to the nx, where it will bring the entire power to the front, as nx is equal to ln of 4.2 plus t over 3. Now note that ln of e will be 1. And let's finish off by solving for x. So then we divide this or multiply by 1 over n. So then x will be 1 over n times ln of 4.2 plus t over 3. And that way we are isolating the variable that we want, that we're interested in. So it's 4.2. Now the next part, it's asking us to create models for an exponential growth or decay. So growth and decay are applications for exponentials. Applications. It's a model. It's an application of exponentials. Now, the difference of these types of applications is if we have a positive growth or an exponential growth, then k will be positive. K will be greater than 0. That constant of growth will be greater than 0. Now, if you have a decay, then k is less than 0, or a k will be negative. So it depends on what type of question or what type of model we are representing. If we have a growth, then k will be greater than 0. If k is a decay, then it will become a negative. So let y be a variable that is changing exponentially with respect to t, and let y of 0 be the initial value of y when t is equal to 0. So that's important. So let's begin by looking at question number 3. Suppose that at 19 years old, you win $100,000 playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under a continuous compounding. So the first thing, you're starting with $100,000 and you have a continuous compound. So that is a type of a growth, right? You're growing exponentially. So it's the formula for a continuous compound is A is equal to P ERT. Now we know we're interested in having $1 million. So A is what you're trying to get at. And then, so there's your, oops, there should be not a billion, a million. Oops, 1, 2, 3, and then 1, 2, 3. Oops. There's something wrong with my pencil here. Sorry about that. So then I have A to be 1, 1, 2, 3, and then 1, 2, 3. Now the time is how long it will take you. So you're retiring at age 67, but you started when you were 19. So that's actually a period of 48 years. So make sure that we understand that. How did we get 48? So your initial time was not 0. Your initial time was 19. That's your starting point. At 19 years old, you earn 100,000 and you want 1 million by the age of 67. So that is a total of 48 years. Now, if you are trying to rewrite it as a formula and solve for the rate, so you want to solve for R. So it's going to be 1 million is equal to 100,000 e to the 48R. And then you isolate your exponential. So then we divide both sides by 100,000. Oops, 100,000. That will give us 10 is equal to e to the 48R. Now, how do you undo an exponential? You're going to take the ln of 10 is equal to 48R ln of e, but ln of e is 1. So you get 48R is equal to ln of 10. You divide both sides by 48. And that means that R is going to be roughly 0.048. But as a percent, that's 4.8%. This is after estimating. Okay, so you round usually to 2 decimal places. Sorry, or 3 decimal places on your rate. Okay. Now, number 4, it's separated into 3 different parts. And let's go ahead and answer this few questions. So number 4 says, according to a study published in 2012, Burmese pythons are becoming the new top predator in Florida. Not many animals in Everglades can stand a python that can grow up to 23 feet and weigh over 200 pounds. So we have 20 pythons were recorded as captured or killed in 1995. Now, by 2009, the number of increased to 378. So write a function of the form P0 e to the RT against C. So this is a growth. It's a growth. We're seeing the number of pythons that have been killed or captured have increased. So we are going to see K, that exponential factor, to be a growth factor. So they're asking us to use this function as a representation of pythons that have been killed after a few years. So you had P of 0, your initial amount was 20 pythons in the year 1995. And then 14 years later, P of 14 years later, because the difference between 2009 minus 1995, that's 14 years. So after the 14th year, you were already of 378. That was the amount. So if we're looking for P of t of P of 0 e to the RT, well, we notice that the P of t, the value that they've been killing is 378, is equal to the initial, which is 20, e to the rate. After how long? After 14 years. So then here we first isolate our exponential. We divide both sides by 20. And 370 over 20, it's going to give us 18.9 is equal to e to the 14R. Now we are solving for R. We're interested in finding the rate when we take the ln of both sides, because we have an ln of 18.9 is equal to 14R ln of e, but ln of e again is 1. So then we get R to be ln of 18.9 over 14. Once we round, we get 0.21 or 21%. So then the general form is P of t is equal to 20 e to the 0.21 t. So that's the general form of this equation. Now we're going to use this model from part A to approximate the number of pythons in 2017. Again, now in our initial year, the initial year was 1995. So then T is going to be 2017 minus 1995. And that's going to be 22 years. So now you're finding P of 22. So how many were killed after 22 years or in the year of 2017? So you're going to substitute 22 as T in my model. So it's 20 e to the 0.21 times 22, like so. And then if we plug this on our calculator, so let's go ahead and do that. Let me project, calculate 84. That way you can also see what I'm doing on my end. So if I'm in my screen here, there's my screen. And then I will have 20 and then E. So there's second E raised to the, put some parentheses, 0.21 times, and then this should be 22. And that's 2029.88. So roughly that's 2030, 2030 snakes if we're rounding up. So we round up. So that's roughly 2030 snakes. Okay. Now the next question is asking for if the ratio of pythons living in the wild captured or killed is approximately 1,000 to 1, how many pythons were estimated in Everglades in 2012? Well, now in 2012, you have to look at the time between 1995 and 2012. Now let's subtract and we will get 17 years. Now we want to find, okay, well, how many pythons were killed in 2012? So P of 17. Again, it's very similar to what we did in B. So it's going to be 20 e to the 0.21 times 17. We want to see how many snakes were killed. It looks like it's going to be 710. They were either captured or killed. Now it's saying if it's 100 to 1, well, 710, oops, as a ratio of 1. Now that means you're multiplying it. You're multiplying 710 times 100. That's 71,000, right? 71,000 snakes. Well, the ratio serves that for every 100, one of them are estimated to be in Everglades. So that's roughly 71,000 snakes. That's a lot of snakes. Okay. In Everglades. That's how many were in there. Number 5 is another model that we have. A sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. How old is the sample round to the nearest year? Now for this one, we want to use a radioactive carbon dating. We're noticing that it's going to be decaying because look at the K. K is less than 0, so it's a decay. It's a decay model. So we're going to use the model where K of 0 is the original quantity for carbon. So the original quantity for carbon is given. So 2%. So we have 2% is equal to 0.02. That's going to be our Q of T for our initial. So Q of T, it's 0.02 Q of 0 is equal to Q of 0 e to the negative 0.000121 T. And now we want to find T in years. So we isolate T. We divide by Q0, we get 0.02 is equal to e to the negative 0.000121 T. We want to take the ln of both sides, so we have ln of 0.02 is equal to negative 0.000121 T. Now we isolate it and we get t to be equal to negative point, oops, let me go back, negative ln of 0.02 over 0.000121. And let's go ahead and plug this in our calculator to approximate the time. So I'm going to clear this out. And I will have negative, which is the bottom, ln of, there's ln of 0.02. So I'm going to take that number, and then I'm going to divide that number by 0.000121. And that should be 3,000, or no, 32,330.76. So for us, that would be 32,331 years. So it's 32,331 years. Now, the last part is to look at a logistic growth model where it's a function written in this format. Y is equal to C, a constant, over 1 plus a to the negative bt, where a, b, and c are positive constants. And notice C, you have a negative b of t, so you'll have a logistic growth model here. So we will see something called the point of inflection here, where it's actually increasing the rate of change of decreasing. So here how it's increasing and then it decreases. So it's up and then down. So once it's changing, so concave up, concave down, that means the point of inflection is where it starts changing from increase to decrease. And then you have this line y equals c, where that denominator, this becomes a 0 and this becomes a 1. So it becomes a y equals c, and that horizontal line. So looking at question number 6, it's asking us to look at the population of LA in millions can be approximated by the logistic growth. So see how it's increasing first and then it's decreasing and being steady. So it's represented by the function 3.194 divided by 1.14.589. This is given. We're trying to find the number of year in 1900. So that means that we're going to be evaluating P of 0, or our starting point, so P of 0 is 3.194 over 1 plus 14.589 e to the negative 0.052 times 0. Well, this becomes a 1. E to the 0 is 1. So this becomes 3.14 over 1 plus 14.589. Let's punch this on our calculator, and that rounds to 0.2048888. So now this is in millions. So that means that your reality had 204,888 people in LA in 1900, which I doubted by that time by 1,000 by the year 1900. Now we're going to now use the same for the population of LA in January of 2016. So that means, okay, well, how long has it passed since 1990 up to 2016? Well, that's the time is 116 years has passed. So now you're going to let T be 116 years. So P of 116 is going to be 3.194 over 1 plus 14.584 e to the negative 0.052 times 116. So let's go ahead and use Wolfram Alpha or a calculator to help us identify the value. So I'm going to open up my screen here in a moment. And project my screen. So I will have my numerator here to be 3.194. And then downstairs, I'm going to use a parentheses because I'm going to need it. And then in my parentheses, it'll be 1 plus 14.584 and then e raised to the parentheses negative 0.052 times 116. Close it. Oop. And then hit enter. So it should look like this. And that's roughly 3.08 million people. So that would mean that we have 3.09. If we round up 3.09 million people in LA. If we round up 3.05, so that goes up to 3.09. So that goes up to 3.09 million. And that again is a type of a logistic model that's represented um, a logistic growth function for a population in LA. Again, this is very vague. Definitely by that time we have more than 3.09 million people, but it's an estimate. Alrighty, for the last two things we have to do is we're going to be using the graphing utility for an exponential growth. So here more is about working with your calculator and learning how to insert data and then find the best logarithmic model regression. So what we're going to do is we're going to go ahead and go to our graphing calculator, and then you're going to input the values for L1, stat, edit. So what I did is stat, edit, enter, and then remove the values. So go to L1, highlight it, and then hit delete, L2, and delete. All I need is the first um, set of points, L1 and L2. So 1, 2, 3, 4, 5, and then 6. 1, 2, 3, 4, 5, 6. And then my values is 6.25 and 16.99. Oh, 16.99. And then I have 46.20. And then I have 125.48. And then I have 341, 341.35. And then I have 927.89. And those are my two logistic points. Now I'm going to go to stat and then calc. And then I want to do a log regression. LN, a linear regression. No, I want a logarithmic regression. So I need L1 and L2. And let's see the plot X and Y. Oh, we have this, we don't have the same link. Let's see, it's stat, edit. Oh, I was missing an input. Sorry about that. So that's 927.89. Oh, I thought I had it. Oh, so now they're all both the same length. So stat, calc, and then we want the logarithmic regression, ln reg, and then there it is. So my function will be a plus b ln x. So all we're going to do is we're going to copy a plus b ln x. So it's going to be negative 17 point, or negative 176.97 if we round, plus b is 383.92, so 9 ln of x. And that's that model that represents my value. Oh, it's saying an exponential. Sorry about that. So this one is an exponential regression. If we wanted a log, then we did a log. So let me go back to this one. So stat, calc, and then we want an exponential regression. Exponential, exp reg, that's the one that we want. So that's y is equal to a b to the x. So they're asking us for an exponential regression. So then A is roughly 2.299 or 2.3. And then B is going to be 2.71. So in this question, they're asking us for an exponential regression. So then all we have to do is substitute into our formula to find that exponential regression. So it's going to be y is equal to the multiplication between 2.299 times 2.17 to the x. So we'll have 2.299 times 2.71 to the x. And then the next one, so let me go ahead and share my screen here. Let me see. So we would have this value, y equal a to the x to the b. So a times b to the x, there's a, there's b. So this should be 2.71. It's a little bit blurry to the x. And that would be our formula for this question. Now, same business, we want to use a graphing utility for now a logarithmic. So the first one was an exponential. So we did exp. So we did stat. So we did stat and then edit. And then we did L1 and L2. L1 is X, L2 is Y. And then we hit calc. And then we did exp, that exponential regression. Now for logarithmic regression, you saw what we did. It's the first thing we did actually. So if we go back to our calculator, for this one, you're going to go into stat, edit again, and then you're removing L1. So you're going to go to L1, delete, L2, delete, and then you're going to input the new values for X, which is 2, 5, 8, 11, and 14. On the other side, on Y, it's 3.75, enter, 5.40, enter, 6.24, enter, 6.82, enter, and then 7.25, enter. Now I'm going to go into stat, calc, and then now this one's the logarithmic regression. So you're going to go ln reg, enter, enter. So this is going to be y is equal to a plus b ln, b ln x. So then you input the values you find for a and for b. So in this case, it's y equal 2.5 plus 1.79 or 1.8 if we round to one decimal, ln of x. And that would be our regression line for our solution. So this is if we round one decimal. Okay. And that represents exactly the function that we have. We can also graph this utility. So you can graph this on Desmos if you like for additional, just to see how it looks like. And with that, we finish section 3.6. Thank you. Bye-bye.